Okay, so we have been discussing connectedness. We have seen the definition. It is just connected is something which you cannot write it like this, some two open sets or something. You cannot have disconnect components. So if we have the set X as union of two proper non-empty proper open sets, then it should be either empty set. One of them should be empty set, the other one should be X. So you can, like drawing this picture, you can get many examples. We want to deal with some particular examples. So this class we will be discussing more examples. Okay. So any non-linear space with respect to the metric coming from the norm is connected, and we have seen that open balls are connected. So, for example, another example is you can remove a point from a metric space, from a non-linear space. If X is a non-linear space, it has a norm and the metric is coming from that norm. Then you can remove a point and this is connected. The proof is direct. Sorry, it's connected provided dimension X is greater than 2. Of course, real line, if you remove a point, it's not connected. And whenever you deal with non-linear space, it is like if you want to remove any other point, whenever you want to talk about properties, if you want to talk about around some point, then it's, topological property, then it's enough to talk about around 0. For example, if you want to talk about whether the open ball is compact or something, then it's because translation is a continuous function. So if you can prove something near 0, around 0, then by translating you can take it there, and translation topological property will be preserved under continuous man. So it's enough to consider near 0. So if you remove any point, that's also connected. Okay? So you can consider 0. So why is this connected? So this is dimension X is greater than or equal to 2, and we assume that X is over R. If it is C, then if it is over C, then C itself is, if it is over C, then dimension 1 is also this property holder. Okay. So if dimension X, so if X and Y are 2 points, so we prove that it's path connected. We have proved that path connectedness implies connectedness. So enough to prove, this path connected. We proved that it's path connected, so it's connected. So X, Y are 2 points in X minus 0. Okay. If X and Y are linearly independent, suppose, assume X, Y are linearly independent, okay, then of course, then this function will do. Gamma of t equal to Tx, maybe 1 minus t x equal y. So this will not be equal to 0. This will not pass through 0. If it is equal to 0, if gamma of t equal to 0, will imply X, Y are linearly dependent, right? Dependent. So because of that, this gamma of 0, 1, this is dependent on t in 0, 1, of course. Okay. Gamma of 0, 1 will be completely contained in X 0, 1. So if X and Y are linearly independent, then they can be connected by this path. So if they are linearly dependent, so second case, if X, Y are linearly dependent, then of course there exists another Z in X minus 0, which is linearly independent of both X and Y, of course. Then you can draw something, then you draw a line from X to Z and then Z to Y. Then you already seen that you can up to 0, half, you can define it to be that, and so exercise. This is it. Okay. So we have proved this. The last class, someone asked whether if you have a non-linear space in R2, for example, it's easier to consider R2. So in R2, mine is a countable set, whether it is connected. Okay. If you, intuitively it is clear, you can remove a countable set, but then countable set may be even dense. Okay, you take all rational points, coordinates coming from rational point, that is dense. So it is not very clear that that can be path connected. But then countable set minus a countable set, okay, is path connected. I will not write the full proof, I mean, in all detail, but it is clear. If you have 2 points in R2, which is not contained in the countable set, then it can be, there are uncountably many paths between them. For example, if you have two, I mean, we can try it in many ways. You have 2 points, then taking this as there are uncountably many circles, for example, between with different radiuses. I mean, circle is an equation with three parameters, right? So if you assume that these 2 points are in the circle, then there will be one parameter remaining, and there are uncountably many such circles. So there are uncountably many circles passing through them, and you cannot have countable many points lying in all those uncountably many disjoint circles, different circles. Right? Or if you don't like it, you can have if you have a 1 point, there are uncountably many lines passing, where the common point is only this point. So you can choose a line which is not in that which does not intersect with this countable set, and you can choose a line. For a different point, you can choose a line. Suppose they are parallel, then you can, so from this point to this kind of countable set, I mean, I'm leaving it as an exercise, you will write all the details. Okay? From this point to this countable set, if you take the distance, that distance is a positive number, but there will be countably many values, right? Because it's a countable set. So you can take a value which is not in that countable set. You can take a circle, okay, which is more than the distance, something, more than this distance between this line. Then you can go to that circle and come back to this. And there are many ways of proving this. Okay, so this is just clear. Even if you take maybe a countable point, countable set, this is clear. Next example is this is GL and R, which is all those matrices in M and R. Okay? That the A is invertible. This is not connected. I think we have discussed this already, but still for completion, I'm saying this. So you can consider this function determinant, which is from all M and C, M and R, okay, to real line, of course. This is a polynomial in n variables, so it's clearly continuous, right? It's continuous. And this set is, I mean, you are on M and R, you are identifying with R n square, right? You are taking that topology, coordinate weight. You can take any norm on this, that will give the same topology. Because this is a finite dimensional vector space. We have proved that in finite dimensional vector space, all now, I mean, coming from all norms are equivalent. They are same topology. So you can take any topology, and the topology is point-based convergence topology. Something convergence different only with converges for each point. So you can identify this as R n square. This is with respect to this topology, and with respect to this topology, this GL and R is nothing but determinant inverse of these two sets, minus infinity 0, union determinant inverse of this function, inverse of 0 infinity. Of course, these are open sets, this is a continuous set, these are, so this is union of two disjoint proper open sets, so this is not connected. Okay? So this is not connected. Okay. So next we want to say, we have seen that if something is path connected, then it is connected. And we have seen that some set is open and connected, then it is also path connected. We have proved that. So only we want to give a counter example for some set which is connected but not path connected. Two examples. I will give two examples, okay, to just give a flavor of it. So one example is you take this set 1 by n in natural number, okay, cross, this is in R2, in R2. We give a set in R2. Okay. I mean, in our real line, there is nothing because any connected set is going to be interval and that's already path connected. So there is nothing. Okay. So in R2, we take this cross this set. Okay. So then So it is just this thing, right? One, it is just this line, and then this line, and this line. It goes on like this, goes on like this. So 1 by n, it is just 1 by n, the point 1 by n plus 0, 1. Okay? 0, 1. So it's like some sort of comb. Okay? And okay. So you call this as K. I mean, call this as K. Let me call this as K cross E. Okay. So my set E is this. E is that set is K. I mean, I call this as K. Okay. K cross this union. I take one single point. 0. Notice that E closure is this set K cross 0, 1, and then it will include one more line, which is just 0 cross 0, 1. No, I have to add something. Sorry, this will not work because this is not connected. So this union, I take this x-axis 0, 1 cross singleton 0. So it is this set. I take this whole thing and then, I mean, it's like a real form. I take this whole line and then take these lines. It's like this. Okay. I take 1 by n cross this line and then I take this line. I mean, and then I take this also line off. Okay. And its closure will include this line off. Okay. What is? No, it is 1 by n. I'm sorry. 1 by n, not yn. Okay. Yeah, 1 by n, n in n. Was it looking like yn for you also? No. Okay. I said 1 by n, 1 by n. Okay. Okay. So you call it E or something. Then E closure will be E union this set 0 cross 0, 1. It will include this line also. That's all. That will be the E closure. That is clear. Right? This is a closed set and that includes that. Okay. So now we have proved that. So now notice that E is path connected. Because if you have 2 points, you can come through this and then you take this and then it's clearly E is path connected, right? So E is path connected. E closure is also path connected, but E closure is also path connected, but we don't need it. Okay? So E is path connected. Indeed, E closure is also path connected. It's also path connected. So in particular, E is connected. So if we have a set F which is contained in E closure, which contains E, okay, then it is connected. Okay? Then F is connected. We have proved this. So let us take this F to be E union just one point, which is this point. 0, exactly 0, 1. This singleton point. I mean, you can take many other points also. Let us take this point. Okay, which doesn't. I mean, we can take any set which doesn't include 0. Okay? So we want to prove that this is of course connected by our earlier proof. This is connected. We want to prove this is not path connected. Okay? So suppose we want to get a contradiction if it is path connected. Suppose if this path connected. What does it mean? Then this point and assume. So let x equal to this point, which is 0, 1, and y equal to this point, the 1, 0. At p cube, x and y are confusing because the coordinates are x and y. So let me change it to p and q. Okay, and are connected by these 2 points are connected by by some gamma function. Gamma is a function from the closed interval 0, 1 to R2, where gamma of 0 is that, gamma of 1 is this. Okay, connected by gamma. Okay, and we want to get a contradiction. Okay, So now you consider this gamma inverse of singleton, that point is 0, 1, 0, 1. Okay. This is a closed set, of course, closed set containing in 0, 1. Okay. So it's compact, the compact set. Okay. So there exists a maximum in this set. Okay. Let T naught equal to maximum. Gamma inverse of this 0.01. Okay. So now my claim is, I want to say that claim is there exists some number T1 which is strictly greater than T naught. So, I mean, we have that gamma of T naught is going to be again, of course, 0, 1 only, this point only, because that by definition. There exists a T1 greater than T naught such that this gamma of this whole thing, because I want to contradict them, use the connectedness and everything. So I take this T naught, this open interval T naught T1. Okay. This is contained in whatever I call as K. K is that 1 by n set. Contained in K. So this is my claim. If not, if that does not exist, so there is T1 here, 0 is here, T1 is here. From up to, I mean, from this is the supremum where, I mean, up to here, gamma of T naught is this point. So after this, I want to say that there is a single interval where this gamma of this T naught T1, this T naught T1 is completely contained in K. Okay. If that is not the case, that means that any interval you take, there will exist a point. Right? That's what it means. I mean, there exists an interval such that this happens. This does not happen for any T1 means for all interval, there will exist a point below that where this is not in K. Right? So there exists a Tn, which is converging to T naught, of course. If not, if this is not true, if the claim is not true, if the claim is not true, then there exists a sequence Tn such that Tn converges to the T naught. And gamma of this Tn is not in K naught. Gamma of Tn is not in K. Okay. That means gamma of Tn has to be along this line, right? Along this line. This line is 0 cross. This implies right. So gamma of Tn is here. But then, I mean, then so P, but then Py, the projection onto the y coordinate, projection of this y coordinate of this gamma of Tn is 0, right? So Px, projection onto, this is projection onto the y coordinate, the Py is the projection onto the y coordinate. Okay, that acting on this gamma of Tn, which is equal to 0, of course, right? Because that's not in K. Okay, so but then Py of gamma of T naught is going to be 1, right? Yeah, Py of T naught is going to be 1, which is not possible because gamma is continuous, Px is continuous. Not possible. Okay, so this is not possible. This gives a contradiction. Okay, so the claim is true. Yeah, what I did is the following. I'm just saying that there exists a maximum T naught. So after that, it's not in this point anymore. After this point. Okay. Now I am saying that after that, it cannot, it has to be in one of, after this, it has to be in one of these things, I'm saying. Okay, because this point is somewhere here. It's just clear. The point is somewhere here. Something cannot come here and converge to that. Okay, so it has to come from one of these things. That's what I'm saying. So the question is, I mean, the point is there is an interval, whole interval T0 up to Tn, such that gamma of T0 Tn has to be in one of this K. K is this thing, these slices. It has to be in that. Okay. If that is not the case, then there exists, of course, for each interval, I'm saying there exists an interval. Suppose that interval doesn't exist, then for each T1, there exists something after this, which is not in that K. So that is what I have assumed. Something gamma of Tn is not in K. Gamma of Tn is not in K means it has to be along this line because that is what I have taken. This is the K. This is my K, right? 1 by n is the K. I mean, sorry, not K means K. This is my K. This whole thing is K. Sorry. I said K, but this whole thing is K. Sorry. This whole thing is K. If it is not in K, it has to be here. So the y coordinate has to be 0. Okay. But the y coordinate of T naught, gamma of T naught is 1. So everything is continuous, it cannot come, right? So that is the contradiction. Okay. So the claim is true. Okay. So now again we can do the same thing. So this implies there exists here. But then T naught T1 is connected, right? Okay. So gamma of this T naught T1 has to be contained in the K. K is this that set 1 by n. N is n cross this 0 1. It's a connected subset. Gamma is continuous. So it's connected. This is connected, right? These are all disjoint connected set, countable union of connected set. So it has to be one of those sets. Okay? It cannot be, I mean, union of two. This implies Px of gamma of T naught T1, this interval, okay, has to be some 1 by n naught cross 0 1 of this. Okay. Again, this cannot happen. I mean, some fixed 1 by n naught, right? This is a connected set, so it has to be one of those arms, right? So this cannot be a connected. This. So again, if you take the Py of this, I mean, yeah, Px is in one of those things, okay? And of course, Px, I mean, okay. Now let us take some Tn converging to T naught, okay? Then gamma of Tn should converge to gamma of T naught, okay? And Px of gamma of Tn is going to be 1 by n naught for all n. Okay. On the other hand, Px of gamma of T naught is going to be 0. Yeah, 1 by n naught, not 1 by n. I mean 1 by n, fixed n naught. So this also cannot happen. I mean, we are using the point is there is a continuous gamma which will not be there. It is also a contradiction. Okay, so this is a slightly different example. Usual example is this. The very standard example for set which is connected but not path connected is usually this set. You take x sine 1 by x, where x is in of course from 0 1. X is sorry 0 1. Okay. And then you take the union of this 0 plus minus 1 1. I mean something like this. You take something sine curve like this. Something I will not draw well. I mean, it'll go on like this. This is of course path connected because itself is a path. If you take any finite thing is path connected. I mean this set is path connected. But you so in particular this set is connected. You can prove that its closure is this whole thing. Because if you want any point here, you can get this point here converging to that. You can find something very close to this, which it will be part of the proof anyway. Okay. So this set E, I mean this you call this as let me see. We call this as E. Okay. Then E closure is going to be E union this set 0 or sorry singleton 0 cross minus 1 1, right? That will be the E closure. Actually, you can take one single point here or some subset of this, and it's easier to prove that that's not connected. That's more easier. You can imitate this proof. But when you want to do E closure, I mean, this is actually a proper, I mean, here is an example. You have E which is not path connected, E which is connected. E closure is also E is connected and path connected. E closure is also path connected, but some subset is not path connected. Here you will have a set where E is path connected, so it's connected. E closure is also not path connected. And any subset, I mean any subset between E and E closure is also not path connected. So that also you can prove. So E closure is not path connected. Why is that true? Okay, so let me try. So let again P naught equal to this is supremum or infimum. Let me take the infimum the other way. Infimum of so suppose there exists a gamma. So the you take this point 0, 1, suppose 0, 1, and that point 1 sine 1. This is another point are connected by some gamma. Okay. Then let again T naught equal to infimum of t greater than 0 such that t greater than 0 such that gamma of t then is in E, of course. E is this set. Okay. X sin to gamma of t square. Okay. So below t there is no such element such that gamma of t is not there. So it has to be in this. So for t less than t naught, gamma of t is in this set, right? 0 cross this minus 1. Okay. This is a closed set. So you can take a Tn converging to T naught, then gamma of Tn will converge to gamma of T naught. So which will imply that gamma of T naught is also in that set. Hence closed. Okay. Right? This is a closed set. Okay. I mean, for all T less than T naught, this is true. That is in this set because that is the infimum. Okay. So you can take a, so for T equal to T naught also, this is true. Gamma of T naught should be in this set. Now let us get a contradiction. So gamma of T naught should be there. So gamma of T naught should be equal to some 0 y naught, right? Some y naught for y naught in this minus 1, 1. Okay. So now let us use the continuity again. Yeah. So what we have, it should be gamma of T naught equal to 0 y naught. Y naught is minus 1, 1. Then let's have some Tn decreasing to T naught. Okay. And gamma of Tn Tx. I mean, gamma of Tn is in that set E. By definition, right? Why is the infimum? Because at zero it is in that way, 0 y naught. No? No, there is no. I didn't. Did I assume gamma of T naught equal to 0? Why the infimum is? No, it's okay. So it can be. I haven't assumed that it's not 0. Yeah, where is it? It's not being assumed. Yeah, we have not assumed. Okay, so it's okay. We are only assuming that. So because that is an infimum, there exists a Tn going to T naught such that gamma of Tn is in that E. Okay. No. The point is, no, that's not the point. The point we have to use the connectedness, right? So, yeah. I mean, again, we have to. So, I mean, you have to go through the same argument to prove that there exists a. So I want to prove that there exists. So, okay, let delta be greater than 0. Okay. then between gamma T naught and T naught plus delta, there exists something, there exists a say term T prime in this, such that gamma of T prime contained is in E. Okay. So here, and where am I using the connectedness? We have to use the connectedness somewhere. Yeah. So if you take, yeah. There exists T naught such that gamma of T prime is in E. So, I mean, the point is this happens for all delta. For all delta, this happens, right? Huh? Which line? Gamma of T naught equal to this. That's because, I mean, this is a closed set, no? Compact set. So maximum is attained in that set. So there exists a T naught such that this happens, right? No, that was earlier at one. I'm sorry. No, I'm not talking. This is not about closed set. What is the infimum T naught equal to this, and no, this set is closed set. Okay, so you can take it some Tn less than Tn for any Tn less than T naught. I didn't write it. I just said it, right? So for any Tn less than this T naught, okay, this gamma of Tn is in that set, in this kind of set, okay, 0 class 0. Okay, now Tn can go to T naught. Gamma of Tn should go to gamma of T naught. So gamma of Tn is in this set for all Tn. So gamma of T naught should be there. It's a closed set. In this set means it means this, no? Gamma of T naught is in this set. This set is 0, some y naught here. That's what I mean. I just spelled out the definition. That's all. Okay. So this is not the gamma of T naught is a tuple 0, and there's no interval. It's a tuple 0 y naught. Okay. Gamma of T naught is a point. Okay. Now I want to say that, see, this, I mean, for all delta, there is something smaller than the T naught. Something this happens, right? So there exists something very near T naught. I mean, this just implies that there exists something very near T naught, okay, however close you want, okay, such that this gamma of T naught, I mean, I want to say that gamma of T naught, some T prime, is in E. Okay? This is what I want to say. This is my claim. Let's forget about this. This is my claim. Gamma of T naught, T prime is in E. If that is not the case, there is some point I'm missing. If this is not the case, then there will exist a sequence which is in E complement. That doesn't seem to contradict anything. Do you see why? For any delta, there will exist something such that this happens, right? You can see that it can take infinitely many values, but I want to prove that the whole interval is clear. And then I wanted to use the connectedness to prove that it will attain all the values from that sin x, sin 1 by x. And I want to get a contradiction that it cannot be true or not. So I want to prove this statement. See, for infimum means for each t naught, there exists a, let me write the definition. For all delta greater than 0, there exists a t. That's what infimum means. Right? There exists a t prime in this interval, t naught plus delta, such that gamma of t prime is in, right? That's what the definition of this is. So gamma of t naught is not there. So let's assume that let me take any very close delta. Okay, I mean what I'm saying is, so for all delta delta prime, for all delta prime, okay. So there exists a t in t naught plus t naught plus delta, and t prime in t naught delta plus t naught delta. Let's assume that delta is less than delta prime, such that this gamma of t prime, both are in. First you get a t prime, then you go smaller than the t prime, and you can do this. Okay? This will imply that gamma for all delta, there exists a t smaller than this delta, such that gamma of t prime, okay? This, I mean, this says that gamma of t, yeah. So now gamma of, so if you take gamma of t and gamma of t prime, that's a connected set. So it should take all values between gamma of, it should take, so what I'm saying is gamma of t is a connected set. Okay? So there exists a Tn in this interval t prime. Okay? Such that gamma, sorry, for what I want to say is gamma of t has, then between this t, let's assume that sine 1 by t. Okay. I'm saying that between t and t prime, this there should exist a continuous value which is in, right? It should attain all that value. Gamma of t should attain all the value. Gamma of t is a connected set. Okay. So px of gamma px, right? Px of gamma of t prime is connected. Okay, let me say this, connected. Okay. So it should take all values between t and t prime. Px of gamma of t, px of gamma of t prime. Okay. And t can be as close as you want. Okay. From this, one should be able to get a sequence. Let me give write the rigorous proof next time and give it to you. Okay. From this, one should be able to get I didn't work it out before. From this, you should be able to get it. If you have some y naught, t naught is y naught, then you can at a distance. It requires more detail, right? So then you can take some sequence here which will converge to here, because it will take all those t naught. No, for example, 1 by 2 pi n plus some theta. This goes to 0, but it will be sine theta for all those things, and this will repeat infinitely many times there. Okay? So you will get some sine theta here, which is not equal to that y naught. Okay? I will make it more rigorous next time, or I will write a proof and send it to you, or I will see it, check it in some book. Okay? I'm sorry, I didn't prepare this, but I have given an argument. Okay. So this is an example of something which is connected but not part connected. The next I want, so we discussed about GL and R, invertible matrices, real invertible matrices, that's not connected. But the complex invertible matrices are connected. Okay? So to prove that, I use this proposition. So let P small p be a complex multivariable complex polynomial in n variables. Okay? In n variables. And let kernel of P equal to all those z1 up to zn in Cn such that P of that z1 up to zn, or let me call it z tilde equal to this, P of z tilde equal to 0. Okay? And if you have multivariable complex polynomial, then its zeros can be infinite. It can be uncountably infinite also. Even in two variable, it can be uncountably infinite. Okay? So Cn, then Cn minus, if you remove this kernel of P, is path connected. Of course, if it is a one degree polynomial, one variable polynomial, single variable polynomial, then it is finite. Of course, the zeros are finite. But if it is multivariable, then it can be infinite. The kernel, the zeros can be infinite. This is the zeros of the polynomial, which can be infinite. So proof. So I want to prove that this is path connected. Let xy be in Cn minus this kernel of P. Okay. I'm using the kernel, which is not the nice word. Usually it's used for homomorphism. Here I'm using for zeros. Okay. Maybe z. Okay. Z of okay. Zeros of P. Okay. So I call it x tilde y tilde, or z tilde w tilde. Z tilde w, or two n complex tuple, okay, which are zeros of this polynomial. Then I want to connect it by a path. Okay. So here is the idea that P of Z equal to Z tilde 1 minus Z here. 1 minus Z tilde, the Z W tilde, where Z is in C. Sorry, gamma of not P, gamma of. This is not a line. This is a gamma is a function from C to that Cn. Okay. It's a function from C to Cn. Gamma of any Z is 1 minus Z tilde Z W. Of course, gamma of 0 is Z tilde and gamma of 1 is W tilde. Okay. These are 2 points in that which miss this zeros. Okay. Then if you compose it with that polynomial, now P of gamma of Z is a one variable polynomial, okay, single variable polynomial. And the zeros of P of gamma Z is finite. Is finite. So if you take gamma of P minus that gamma of C is in Cn minus the Z of P of gamma P composed with gamma. Okay. Cn minus this. Okay. This is contained in Cn minus that Z of P, right? I mean, for something which is not in the zero, it's not going to be a zero, so it's not in that set, right? Okay, this is contained in that set, and this is path connected because this only misses finite points. This is path connected. So they can be connected by a path. So in particular, Z tilde and W tilde can be connected by a path, connected by a continuous path. In this set, of course, that means in this set also. That's enough. So corollary to this is this GL and C, which is all those matrices in M and C. A is invertible. Is connected, is path connected. Well, then this is proof. This is equal to, I mean, Cn square. This can be identified with Cn square minus zeros of this determinant, which is a polynomial, right? Determinant the complex function is the zeros of that, right? So which is connected because of that. Okay. There can be more examples, so let's stop here. So can I take more time? I mean, I have 15 minutes because I wasted some time there. So if you feel tired, you tell me, I'll stop. Because I want to discuss what is called Cantor set. I may not have more time. I mean, I already missed a class. So I will finish this in this. Okay. So next we want to discuss, I mean, is set, we defined something called totally disconnected set, and we haven't seen an example. We haven't seen a closed example. We have seen rational numbers are one example, but that's not closed. So we want to see an example which is closed. So Cantor set is an example for many, many things. So this is so I will start here maybe. Actually, Cantor set is just you take 2 points, 2 point set, and take an infinite, countably infinite product. It is basically that. But we want to identify in a particular way as something contained in the interval 0, 1. So this is Cantor set. So you take the interval 0, 1. Okay. Then you take I1 to be this interval 1 by 3, 2 by 3. Okay. Then you take the C1, you define C1 to be C0 minus I1, which is this 0, 1 by 3. This is the union of this closed interval. Union 2 by 3. Okay. Now you divide this into, so we have taken this interval, divided into 3 parts, and we have removed the middle part, middle open interval. Now you divide this interval and this interval into 3 parts, remove the middle part, and inductively do this. So if Cn equal to union, disjoint union of I equal to 1 to 2 power n. So here there are two intervals. C1, there are two intervals, 2 power 1. So I equal to 1. II will not be a nice idea. So what is Ji? Some Ji. Or we know how it looks, right? So equal to this closed interval I by 3 power n, I plus 1, 3 power n plus 1. That's how it will look, right? So where I equal to 1 to 2 power n, right? There are many, there are 2 intervals here, then there will be 4 intervals. We are going to take 2, right? Some I and I plus 1. All I may not occur. I equal to this may not be right side. Yeah? I in some set I. Okay. You may not get all of them. So here we are getting 0, 1, 2, 3. You will not get that. Okay. Now you define C n plus 1 to be the same I in I with I 3 power n plus 1, I 3I, 3I plus 1 by 3 power n plus 1. Okay. Union 3I plus 2, 3 power n plus 1 plus 3I plus 1, which is 3I plus 1 by 3 power n plus 1. Okay. So each interval, when you have one interval, you've got 2 interval in terms of. So that will have the same form. So you can go on doing this. So if you have Cn, you would get Cn plus 1 like this. So C equal to intersection of all n equal to 1 to infinity C. Okay. This is non-empty. Since it contains all that point, endpoints of all those closed intervals, right? Even 0 is there, for example. You are getting 0 is there, 1 is there. Okay. And it contains all the endpoints of the open closed interval. It's at any point Cn is the union of closed intervals. Okay. In those closed interval, you are removing a middle open. So the end point is there in all those Cn. Okay. So since the endpoints of closed interval in Cn are an element in C. Okay. Because of that, this is non-empty. Okay. Further, it is closed, of course. This is intersection of closed set. So this is also closed. Because it is intersection of closed set, so it is closed. Okay. I'm not writing it, it's there, it's closed. Okay, let us see some properties. So first property is, let us compute the length of interval we have removed. I mean, this when you learn, maybe you have got some idea about measure theory. So you can, there is something called length. You can talk about any set, not just interval. We know the length. This minus this is the length of the interval. So you can talk about, so length removed. So length, we have removed all those I1 set, and then of course some other i's in the next step. So length of intervals removed. I'm not telling you may not know measure theory, but I am just using the concept. Is first one we have removed is 1/3. Then we have removed two intervals of length 1/9. So 2/9. Then we have removed 4 intervals of 3 cubed, like this. Go on like this, infinite like this. So which is equal to 1/3 into 1/1 minus 2/3, which is equal to 1. A geometric series. So we have removed total intervals of length 1 we have removed. So length of that series, I mean, if you, length is an additive function. If you have two disjoint interval, length is an additive function. So you have removed intervals of length, then the length of that C is 0. Huh? Countably additive also. It's countably additive. So I mean, measure is countably additive, length is countably additive. Correct. So because of that, so this is length of C is 0. Okay. So you should expect that this is a nowhere dense subset. I mean, it does not, it's a closed set. So it cannot have any open interval. That's what you want to expect. But let us prove it. Okay. So suppose, so the claim, first claim is C is nowhere dense. Nowhere dense. That is, it does not contain any interval. It's closed. I mean, nowhere dense, the definition is closed and does not contain any interval. Interior is 0. So let x is in C and epsilon be greater than 0. Okay. X is in C means x is in Cn. So choose n such that 1/3 power n is less than 2 epsilon is enough. Let's take less than epsilon. As small as you know. Okay. So, okay. And x is in Cn, of course, for all n. So in particular, x is in Cn. Okay. So now the interval will intersect with the complement. I mean, it is nowhere dense. By this we mean it's nowhere dense in the interval 0, 1. This is the big matrix. I mean, in this matrix, C itself is a metric space with respect to the restricted metric, and it's actually a complete. So there is nothing called nowhere dense for that. It is nowhere dense in this metric space. Okay. So now x is in Cn. So x is in some interval. X is in some interval I/3 power n, I plus 1/3 power n, right? In some interval. Okay. And length of this is 2/3 power n, right? No, 1/3 power n. 1/3 power n. Okay. And if I mean, and we know that this length is less than epsilon. So this implies that x minus epsilon, x plus epsilon, okay, for x in Cn, intersection Cn complement is non-empty, right? This is not completely contained in 0. So this implies x is not an interior. I mean, this implies x is not, I mean, x is not an interior point. Okay? In particular, interior point of, I mean, x is arbitrary, so interior point of this is empty set. That is, it does not contain any interior point. So it's a nowhere dense subset. So you have got a, so you haven't seen yet a nowhere dense subset which is uncountable. This set will be uncountable. The reason is you can argue it in two ways. One is this is next line is C is uncountable. I will give two reasoning for this. One is the problem is correct. Correct. That's what that's one way. Correct. That's what I thought you don't have some problem here. So you are right. Yeah. So that is, so you can see that you are choosing the first element from this. I mean, if you have any x in C, then it has to be in the intersection. So it has to be in one of this set. So if it is in this set, if you write the ternary expansion, it is going to be 0. If it is in this set, it's going to be 2. So the next two again, I mean, so next the same thing is going to happen again. It's going to be 0. So it's basically ternary expansion is going to contain 0 or 2. So in that way, C is you can write, but you have to work more. You have to prove that it's actually a homeomorphism and other thing, okay? Because the topology matters and all that. So that is why I will give you another. So this is one way. 0, 2 is n. This is 0 to 9. Okay? As a topological space, I mean, you have to only prove that from here to here, you write the map. Okay, this is an exercise. You take any, so you take any xn contained in this 0, 2. Okay? Yeah. And define the map phi of the sequence xn equal to summation xn by 3 power n. Okay. This will prove that this is actually in C, number one, and this is on 2, and it is continuous. Continuous with respect to the product topology here. Or if you want really a metric here, you can have a metric here. The metric will be, you can have a metric here, d of any xn, any yn. You can define a metric summation mod xn minus yn. Maybe divided by 2. Divided by 2 into 3 power n, whatever. I mean, so that will become 1. Okay. So this will give a metric on that. Okay. So with respect to this metric, this map is continuous. And for compact set, you need to check continuity only in one direction. The inverse is automatically continuous. Okay. So that is one way of doing it. The other way is to use the Baer category theorem. So I have in actually this was in some question in the quiz or in the exam. I don't remember that. So definition. So X is a complete metric space. We deal with complete. I mean, for the definition you don't need, but let's assume that complete metric space. Then A contains, I have to define an accumulation point. We have defined something called limit point, which is slightly different from the usual definition. So I define A, B some set in some metric space. Then AX belongs to A. X is in X is an accumulation point. Which is the usual definition of limit point. Accumulation point. If for all epsilon greater than 0, the open ball B x epsilon minus this singleton x, okay, intersection A is non-empty. Okay. There exists some element in the open ball other than x which intersects with A. Okay. So there exists a non-constant sequence in A. I mean, not equal to, not the constant sequence x. There is some other. So this is actually equivalent to saying A does not have any isolated point. This is equivalent to saying X is not an isolated point of A, or I mean, it is in the closure, it's not an isolated point. Okay? I mean, the definition, you can take that to be the definition. So a closed set is so definition. A set is set S contained in X is perfect if S is closed, and it's enough to prove S is equal to accumulation point of S. Let's say that AC of S is equal to AC of A or whatever, equal to all accumulation points. This is the collection of all accumulations point of A. The A equal to accumulation point of S is equal to accumulation point of S. Then we call it a perfect set. Okay. So now the theorem is X is complete and S contained in X is perfect. Then S is uncountable. So, I mean, if it is an isolated point, that means you can have an open ball around that which contains only that point. That's what the isolated point. So that point is an interior point. Isolated point is an interior. But here there is no isolated point. So that means that every singleton set is nowhere dense. Okay. So this is because proof is any singleton set X is in S, then singleton X is nowhere dense. Okay. Then S is union of singleton X and okay, no, X is union singleton X, and by Barre's theorem it cannot be countable. So it is uncountable. So now we prove that the Cantor set is actually perfect. So now the claim is the third Cantor set. P is perfect. So what does perfect means? You take an open ball, that's open ball around that X that should intersect with the set. I mean, that intersection should have some other point other than. Okay. So the proof is X is in C, then X is in, so then epsilon greater than 0. Again the same thing. Choose 1 by 3 power n less than epsilon. 2 epsilon is fine. 2 epsilon. Then X is in Cn. In particular, X is in some interval like this, I plus 1. 3 power n. Okay, maybe X is less than epsilon. Now, if you take an open ball around this, okay, this will contain the, no, this is okay, 2 epsilon is fine. So now this, if you take an open ball around this will contain every element in this set. But this will contain infinitely many points from this set because the open interval you are going, so the open interval you are going to remove or the closed interval, whatever the remaining closed interval, all those endpoints are going to be here. Those endpoints are going to be in this interval. X minus epsilon plus x plus epsilon contains all endpoints of the open interval removed or the remaining closed interval. Okay. And there are going to be infinitely many. Endpoints of closed interval in Cm, m greater than that n, okay, and contained in this interval. Okay. You understand what I'm saying? All those closed interval containing in this, which are going to be in the Cm after this, and those are the endpoints of that. There are infinitely many of them that will be contained in all this interval. Okay. So this is a perfect set. Okay. So in corollary to this is Cantor set is uncountable. Okay. So it is an uncountable nowhere dense set. And what else is there? Is there any other property you remember? You know counter set before? Yeah, you have seen it, no? So any other property? So it is totally disconnected. That's so next property is maybe fourth or fifth. C is totally disconnected. I'll stop with this. Okay? So what is totally disconnected means? The earlier definition is if you have 2 points x and y which are different, then there exists a open set containing this point and this point, okay, which are disjoint, and then whose union will contain this set. I mean, union is equal to that set. Or in other words, you can say that the equivalent definition is, I mean, this is equivalently enough to prove. No, I mean, this is easy exercise. Enough to prove. Given for x in C and epsilon greater than 0, there exists a set S contained in x minus epsilon, sorry, B of x epsilon, maybe x minus epsilon, x plus epsilon, intersection C, of course, which is closed and open, which is called a open set or something. In C, of course, in the relative topology. It's enough to prove this. I mean, you have to choose a closed open set. You take this as open set. Its complement is closed. I mean, its complement is also open. So you take that open set. Okay? So if you have any 2 points, x and y, then the distance between them is strictly positive. You take an epsilon which is less than that. Okay? Then you have a closed and open set around that x. Okay? So it is equivalent to the earlier definition, okay? Which is in C. Now it's easy, the same thing. So now we want to find a closed and open set. So given epsilon, so again choose 1 by 3 power n less than epsilon, epsilon or something. Okay. Now x is in Cn and it is in one of those closed intervals. Okay. That closed interval is, I mean, that's closed interval. That closed interval is x minus epsilon, x plus epsilon, intersection C. And maybe it may be bigger. So, I mean, that closed interval is contained in that. Okay. So, and you can choose a smaller epsilon if you want. Okay. So that closed interval is an open set in the relative topology. And if you take the complement of the closed set in that Cn, that is going to be union of closed set which is closed. See, in the relative topology, something is open if it is intersection of some open set and this. It is closed if it is an intersection of closed set in this. Okay. Now I shall leave it as an exercise that it is actually both. You can find a closed and open set contained in this. You have to write it in words. Okay. You take a point and you take that open interval where the point is there. That particular closed interval. That closed interval is open. I mean, that closed interval intersection C is open because its complement is closed. Okay. And it's also it's already a closed set. So it is actually closed also in the relative. So it's both open and closed. So this space is totally disconnected.